In this video, we are to calculate the support reactions and we are to draw the shear force in the bending moment diagram for a cantilever beam with a UDL. So the span of the beam is 10 meters and this point is A and this point is B. The force per unit length of the UDL is 4 kilonewton per meter. First of all, you have to calculate the support reactions. A fixed support has 3 reactions. Call this VA, horizontal reaction, HA, and a moment. You can take it in the clockwise direction and I'll call it MA. So we have to find the unknowns, and these are the support reactions. So let's take moment about point A to be 0. Clockwise moments, we're taking clockwise moments as positive. So MA is moving in the clockwise direction, so it's going to be positive MA. The whole UDL covering the entire span of the beam will cause a clockwise moment. So it's going to be plus 4 times the distance, which is 10. So the force per unit length times the distance is going to give us the force. So 4 times 10 will give us the force, but we want the moment. So the moment, or the whole force, is acting at the middle. So the centroid of the UDL is at the middle, and we'll take the perpendicular distance from the middle of the UDL to where the fixed support is, and that's 5. So times 5. So this is the moment. That's the UDL or cos. Everything here is equal to 0. So these are the only forces which will cause moments. Let's make MA the subject. MA is equal to, when we send everything here to the other side of the equation, we are going to get negative 200 kilonewton meter. And let's calculate for the vertical reaction. Let's take upward forces to be positive. So sum of forces in the vertical direction is equal to 0. VA is moving up, so positive VA. The UDL is coming down, starting downwards, so it's negative. So minus 4 times 10. So 4 times 10 is going to give us the force. Everything here is equal to 0. These are the only vertical forces. Making VA the subject, we are going to get 40 kilonewton. That's VA. Now let's find HA. Sum of forces in the horizontal direction is equal to 0. So let's take forces moving in the right side as positive. So HA is equal to 0, since that's the only horizontal force. We are done calculating the support reactions, so let's deal with the shear force. The shear force is the sum of vertical forces. So the shear force at A, and calculate 2 shear forces. So the shear force at A prime is equal to 0. Then we'll come to shear force at A. This is where we include the existing force acting at A. So we'll pick the previous one, which is 0. Then when you look at VA is moving in the upwards direction, so it's positive O plus VA, and VA was 40. Sorry, so VA was 40 plus 40. So when you sum them, you're going to get 40 kilonewton. That's the shear force at A. So there's the UDL. We can pick the center of the UDL and call this part C. So now let's calculate for the shear force at C. When calculating for the shear force at C, because you are taking the middle of the UDL, we'll calculate only one shear force. From the previous video, I made mention that when you are dealing with the shear force, when you're calculating the shear force in a UDL, you only calculate for one shear force. So shear force at C. So that means you are making a cut at C. So this will be equal to the previous one, which is 40. And remember, we made a cut at C and we are picking this part. So this part will still remain. So the force per unit length of this part is still 4 kilonewton per meter. But the distance will no longer be 10, the distance is 5. So it's going to be plus minus because the UDL is acting down. So minus 4 times 5. So this will give us the force of this UDL. So when we sum this, or when we subtract this, you are going to get 20 kilonewton. And that's the shear force at C. So let's move to the shear force at B. So with the shear force at B, we'll calculate for two shear forces since it's the end of the beam. So shear force at B prime will be equal to the previous one, which is 20. Since you are taking B, this part of the beam will also be included because you are making a cut at B and we are picking this side. So this part is included on the beam. Sorry, this part is included on the beam. So the force per unit length is 4 kilonewton per meter. So the distance from here to here is 5. So it's going to be minus, because it's acting down, 4 times 5 again. So 4 times 5 going to give us 0. And now calculate for the shear force at B. The shear force at B, we pick the previous one, which is 0, plus the existing force at B. There's no point load acting at B. So shear force at B is 0. So now let's draw our shear force diagram. So this side is A, this side C, and this side is B. Shear force at A prime 0, so 0 is here. Shear force at A is 40, so 40 is here. 40 kilonewton. And we'll connect the two. Shear force at C is 20, so 20 somewhere here. We'll connect the two. And the shear force at B is 0. Shear force at B prime 0, shear force at B is 0, so you come back to 0. So this is the shear force diagram and it's all positive. So let's deal with the bending moments. The bending moment at A, let's take the bending moment to our right, our left, sorry. So we'll call this BMA. So it's moving in the anti-clockwise direction, so negative BMA. Then there's MA moving in the clockwise direction, so it's going to be plus MA. Everything here is equal to 0. So when we make BMA the subject, we are going to get BMA will be equal to MA. And we found MA to be negative 200. So it's negative 200 kilonewton meter. That's the bending moment at A. Now let's calculate the bending moment at C. So with the bending moment at C, we can choose to take our left or our right. But let's take our right. So you can take moment. Because I'm taking my right, I'm taking the bending moment to my right. And I'll call it BMC. So BMC is moving in the clockwise direction, so it's positive. So it's going to be BMC the clockwise, and this UDL will cause a clockwise moment. So it's going to be plus the force per unit length of the UDL is 4 times the distance from here to here. That is 5. So this will give us the force. And because you are calculating for bending moments, you take the centroid. So the centroid is at the middle, and the distance from the middle of the UDL to this portion is 5 divided by 2. So these are the only forces causing moments, and we equate this to zero. So 2 will cancel this 2 times. When we make BMC the subject, we are going to get 50 kilonewton meter. Negative 50, sorry, because we'll move this here. So negative 50 kilonewton meter. And that's the bending moment at C. And now let's calculate for the bending moment at B. Bending moment at B is zero because I can choose to take my right. So bending moment at B is moving in the clockwise direction. So it's positive BMB is equal to zero since there is nothing at the right hand side again. So this is the calculation for the bending moment. Now let's draw the bending moments diagram. The side is A, C, and D. Sorry, and B. Bending moment at A is negative 200. So plus negative 200 to be somewhere here. The negative 200 kilonewton meter. We'll connect these two. So let's say the point is here. This negative 200 kilonewton meter. Now bending moment at C is negative 50. So negative 50 somewhere here. Negative 50 kilonewton. And the bending moment at B is 0. But because we are dealing with a UDL, it's going to be a curve, a parabolic curve. So looking at how it's going to go this way. It's going to be a curve. So it's not a straight line, it's a curve. It's a parabolic curve. And it's all negative. So this is the bending moment diagram.